Hello, I'm Nick Huntington-Klein, and today I'm going to talk to you about predictions and residuals in ordinary least squares and how ordinary least squares actually does its thing. So we want to know about ordinary least squares, right? The regression approach, where we're looking for the relationship between an x and a y by fitting a straight line shape onto our data until we get a good fit. So what's actually going on there? In order to figure it out, we're going to need to talk about what are predictions and what are residuals. So we talked last time about how an ordinary least squares line gives us a prediction. If I have a line and I have an x value, I can follow that x value up until I hit the line, and then that's going to tell me my prediction for what y is going to be. That is my prediction. However, we also know that predictions are not perfect. If we go back to the graph we used, we can see that even though that line looks pretty good, it does follow the data pretty well. We also see that there's points above and below the line. The line does not perfectly predict the outcome. Now, what does that mean? It means that there is a residual. A residual is the difference between the actual value and the prediction that we have made, right? So let's say, for example, that I'm predicting your height based on your age. And let's say that I'm going to predict, and let's say we're talking about children here. So let's say that I'm going to predict that 6-year-olds, that's my x value, my x value is age, and my y value is height. Let's say I'm going to predict that 6-year-olds have a height of 4'6". They're 4 foot tall and 6 inches. Okay, so if a 6-year-old walks in who is 4 foot tall and 8 inches, that means that I was off by 2 inches. That 2-inch difference, that is the residual. The actual y was 4 foot 8 inches. The predicted y was 4 foot 6 inches, and the difference between them is my residual. Now, that is basically the error in our prediction. We made a prediction and we were not quite correct. Now, we're never going to be precisely correct, or we're very rarely going to be precisely correct, but we want to get as close as possible. And so what ordinary least squares does is it tries to pick a line that makes those predictions as accurate as possible. It wants to minimize the residuals. And not just that, it doesn't want to minimize the residuals, it wants to minimize the squared residuals. And it does that because, let's say, we have a really big error. We want to make sure that those really go away. We want to pay really close attention to the errors that are far away from our line, because those are the errors that make us think maybe we really picked a bad line, right? If there's something really far off there that we need to worry about. So what can we actually do? What is OLS going to do about this? So let's take a look. Let's start with some data. Let's just pick 4 points of data. It's going to make it really easy to see what's going on. And we're going to fit an ordinary least squares line to this data. So first of all, let's just pick a line. This is not an ordinary least squares line. I just put a line on the graph there. Now then from here, let's figure out what are our residuals. So the residual is the difference between the actual value and the prediction. So I'm drawing a line here between the actual value, which was the dots of data, and the prediction, which came from the line. I used the line to make a prediction. It was wrong. The difference between the line and the point, that is my residual. So I've drawn those in with straight lines here. The next thing I'm going to do, I mentioned we want to minimize the squared residuals, is we're going to take these residuals and we're going to square them. Okay? How do you square something on a graph? Well, you just take it and you turn it into a square with that length of side. So we've got some squared residuals here. Now, I can try different lines, and those different lines will give me different sizes of squared residuals. If I add up the area of all of those squares, I'm going to get my sum of squared residuals. And I'm going to pick the line that gives me the smallest sum of squared residuals. And I can tell you this is the ordinary least squares line, and I can promise you that it is giving us the smallest sum of squared residuals. And that's how it does it. It specifically takes the residuals, squares them, and then it uses calculus basically to find the line that gives us the smallest sum of squared residuals. We can see how this works mathematically. If we think about taking our intercept and slope line that we talked about before, first of all, we're going to add a residual to it to reflect the fact that we are not perfectly predicting. So we have intercept plus slope times x plus our residual. We're then going to turn that into a theoretical data generating process. Okay? So instead of saying intercept, slope, and residual, we're going to use parameters, beta 0 for the intercept, beta 1 for the slope, and the epsilon error term. So we're now into the theoretical world. This is the true model that we are trying to estimate with our ordinary least squares estimation. The error is still there because, even with a straight line, even in the true model, there's still going to be other stuff in the model that we're not accounting for with x. That's going to be in our error term. So from there, we can take our residuals, which are basically whatever we estimate using OLS, and the difference between that estimation, that prediction, and our outcome. We're going to square it and sum them up, So we're taking the residual there, we're squaring it, and we're summing up. That sigma there is 4. We can also point out that the residual is just the actual y minus the estimated y, which would be squared. And also that estimated y comes from the beta 0 hat, which is our estimated beta 0, our estimated intercept, and beta 1 hat, our estimated slope. So you take the actual y, you subtract out the predicted y, which comes from our beta 0 and beta 1 times x, square it up, so that's a squared residual, add all of those up, and then you use calculus to figure out what the optimal beta 0 and beta 1 are. That's the basic idea, right? What we've learned about here are what a residual is, the difference between your prediction and the actual value. So far, so good. We've also figured out how the OLS approach uses those residuals to find a line that best fits the data. It tries a bunch of different lines and chooses the one that gives those sum of squared residuals, remember those squares on the graph, as small as possible. And that's basically it. Thank you.